Hello and welcome to very special episode on crystallography and mineralogy. I am Ashima teaching in the Department of Geology, University of Delhi. Students, first we will talk about the classification of aluminosilicates based on SiO4 tetrahedron. Silicon is known to be the second most abundant element after oxygen, forming the Earth's crust and the mantle. Silicate minerals predominate vast majority of rocks of the Earth's crust, as the silicon-oxygen bond is considered to be stronger than any other bond prevalent amongst oxygen and any other element. As the SiO4 tetrahedral dominates silicate structures, the way it arranges itself within a particular structure has long been the way of silicate classification. SiO4 tetrahedral are either isolated from each other or connected by corner sharing to other SiO4 tetrahedra. The different frameworks provided by variable corner sharing tetrahedra with other cations fitting into suitable interstices provided by this framework defines the various types of silicate structures. This framework of cations and SiO4 tetrahedra is of prime importance in understanding the way in which a mineral would adapt to changes in its physical and chemical environment. Many silicate minerals also show substitution of aluminum for silicon in the tetrahedron, which is accompanied by compensating replacement in cation content to maintain charge neutrality. Based on SiO4 tetrahedral linkage, the aluminosilicate minerals Kyanite, Andalusite and Sillimanite with a composition of Al2SiO4 are clubbed under the nesosilicates. In all the three minerals, chains of ALO octahedral occurs parallel to the crystallographic axis. Each octahedra shares two oxygens with the above and below octahedron, thus giving rise to aluminum oxygen chains of AlO4 composition. The chains are cross-linked by the remaining aluminum and silicon ions. In all cases, silicon is tetrahedrally coordinated by oxygen ions, resulting in discrete SiO4 units with 4 negative charge structural units. The remaining aluminum is in 6-fold coordination in kyanite, 5-fold coordination in Andalusite and 4-fold coordination in Sillimanite. These three minerals are of same composition, but exist as different structures owing to different cross-linking and chain positioning depending on the temperature and pressure conditions, hence are considered polymorphs. They have been widely studied in petrology as they are useful as temperature and pressure markers of metamorphism in crustal rocks. Now, we will deal with the structure and chemistry of these minerals. Kyanite, in Greek word kainos, dark blue substance. The structure of kyanite consists of chains of edge sharing AlO octahedra that are linked together by the remaining silicon, aluminum and oxygen ions, silicon being coordinated by 4 oxygen ions and aluminum by 6 oxygen ions. Kyanite has a relatively dense structure in which oxygen atoms are arranged in slightly distorted cubic close packing. Kyanite has a relatively pure AlAlO SiO4 composition. Minor substitution of ferric and Cr3 plus can be accommodated by the kyanite structure. The small amount of Ti4 positive substitution is due to frequent inclusion of rutile in kyanite. Synthetic kyanite can be produced in lab at a 900 degrees Celsius and 10 to 40 kilobar. The phase diagram of Al2SiO5 composition shows the triple point between kyanite, Andalusite and Sillimanite to lie at about 4.5 kilobars and 550 degrees Celsius. It may invert to Andalusite or Sillimanite by a change in the pressure or temperature conditions. Kyanite also gets converted to mullite and glass on heating to about 1300 degrees Celsius. Kyanite may alter to sericite, margarite or pyrophyllite. The kyanite of regional metamorphism may be involved in number of metamorphic reactions and may show reaction textures with minerals like Andalusite, Sillimanite, Sterolite, garnet and cordierite. Now, we will talk about Andalusite. Andalusite discovered in Andalusia in Spain. It has chains of edge sharing ALO octahedral groups parallel to the C axis. Lateral linkages between the octahedra is provided by silicon between 4 tetrahedrally arranged oxygen atoms alternating with aluminum being between 5 oxygen atoms. The mineral is relatively pure AlOSiO4 and shows substitution of Mn3 positive and iron 3 positive for octahedral aluminum. Extensive solute solution to canoneite is reported for Andalusite with 32.2% Mn2O3 leading to a composition Mn3 plus AlSiO5. The term viridine has been used for Andalusite containing 4 to 8% Fe2O3 and 19.6% Mn2O3. Andalusite can be synthesized from kaolinite or from a mixture of Al2O3 and silica at temperature of 450 degrees Celsius to 650 degrees Celsius and water vapor pressure between 0.6 to 2 kilobars. Alteration to sericite, chlorite and other sheath silicates is commonly exhibited by Andalusite. It also shows metamorphic reaction relations with minerals such as cordierite, sterolite, garnet, sillimanite and kyanite. We will now discuss about Sillimanite, which is after Benjamin Silliman 1779 born and died in 1864, is an American chemist and mineralogist. The structure of Sillimanite consists of edge sharing octahedra of ALO parallel to C axis, double chain of tetrahedra containing silicon and aluminum alternately in fourfold coordination provides the lateral linkage between octahedral chains. The composition of Sillimanite is relatively pure Al2SiO5. Fe3 plus and Cr3 plus may replace the aluminum in the structure. Minor amount of absorbed and entrapped water is found to be present in the fibrous fibrolite variety of Sillimanite. It can be synthesized from its component oxides at high pressure and temperature condition. The triple point between kyanite, Sillimanite and Andalusite lies at about 500 plus minus 50 degrees Celsius and 4 plus minus 0.5 kilobar. At temperatures higher than 1000 degrees Celsius, it is known to convert to mullite and quartz. It is known to be involved in many metamorphic reactions, hence reaction textures with associated minerals are commonly exhibited by it. Alteration product mostly includes muscovite, sericite, pyrophyllite, kaolinite and montmorillonite. Now, we will discuss the crystallographic properties, physical properties, how kyanite looks in hand specimen. It commonly forms columnar or bladed elongate crystals. It has a patchy blue, gray or white and rarely light green color, vitreous to pearly in luster and gives a white streak. It has a hardness of 4 to 5 parallel to C direction and 7.5 at right angle to C crystallographic direction. Specific gravity ranges from 3.53 to 3.67. Cleavage is perfect on 100 phase. Cleavage fragments are usually splintery. Splintery fractures are common and crystals are of brittle nature. A basal parting is conspicuous on 001 phase, cutting at about 85 degree to the length of crystals. Twinning is not obvious in hand sample, though single and multiple twins with 100 composition planes are common. Andalusite in hand specimen, how it looks. Andalusite crystals are commonly elongate prisms with a nearly square cross section. A variety called ceastolite known to display carbonaceous inclusions along the diagonals of the prism. It can also occur as anhedral grains and irregular masses. Mostly are pink, white or pinkish brown in color. Usually gives a hardness of 6 to 8 and specific gravity of 3.13 to 3.16. Vitreous in luster and gives a white streak. 110 phase displays prismatic cleavages and are observed parallel to prism faces in cross sections, though may not be evident in hand samples. Subconchoidal and uneven fractures are common and crystals are of brittle nature. Twinning on 101 composition plane is rare. Now, we will discuss how Sillimanite looks in hand specimen. Sillimanite usually forms fibrous or slender prismatic grains. Color wise, the crystals are either colorless or white. Vitreous in luster and gives white streak. It has hardness in the range of 6 to 8. Specific gravity ranges from 3.23 to 3.27. Sillimanite exhibits a good cleavage on 001 face parallel to length of crystals. Crystals are brittle in nature and may show uneven fracture. No twinning is reported for Sillimanite. Now, we will discuss the optical properties of these minerals under plane polarized light. Kyanite, it shows high relief, are commonly bladed in habit. Radiating aggregates of blades are also common. Usually colorless in thin sections, but may sometimes show pale blue color. Display weak pleochroism with X being less than Y being less than Z, and X is colorless. Y shows light violet blue green color, Z shows light cobalt blue color. Cleavage is perfect on 110 phase. Then we have the Andalusite. It shows moderately high positive relief and is commonly euhedral elongate prism, usually colorless in thin section. Exhibits weak pleochroism. X shows reddish pink color, Y and Z shows the greenish yellow color, and cleavage is good on 110 phase. Now, we have the optical properties of Sillimanite. It shows moderately high relief and is usually colorless in thin section, though fibrous masses can exhibit a pale brown color. Most Sillimanite in thin section is not visibly pleochroic. Cleavage is perfect on 010 phase on basal section of Sillimanite. Now, we will discuss the properties of kyanite under cross polarized light. Kyanite, it is anisotropic in nature, shows very low bright effulgence, shows first order gray polarization colors, shows oblique extension on cleavage, and prism edge are usually biaxial negative. Optic orientation is Z, the angle between Z and C and angle between Y and B are both about 27 to 30 degree, and the angle between X and A is only few degrees. Optic axial plane is nearly normal to 100 phase. The 2V angle is equal to 73 to 86 degree. Usually shows positive sign of elongation on the lens slow direction. Then we have the optical properties of Andalusite. It is anisotropic in nature with a low birefringence, shows first order gray polarization colors, straight extinction on prism edge or on cleavage trace, Basal section shows symmetric extinction, are biaxial negative in nature. Optic orientation is x is equal to c and y equals to b and z is equal to a. Optic plane is 0, 1, 0 for all composition ranges. 2V varies between 73 to 82 degree. Sign of elongation is length fast negative. As for the Sillimanite, it is anisotropic in nature, shows moderate birefringence, high first order to low second order polarization colors, straight extinction on single cleavage trace and are biaxial positive. Optic orientation is alpha is equal to x, beta is equal to y and gamma equals to z. Optic axial plane is 0, 1, 0. 2V gamma varies from 21 to 30 degree. Sign of elongation is length slope positive elongation. Occurrence of these minerals. Each polymorph is known to have a specific pressure and temperature range over which it is stable, with Andalusite being the low pressure polymorph. Kyanite is stable at higher pressures and Sillimanite is stable at high temperatures. So, these minerals have found extensive application in establishing the pressure and temperature conditions of rocks bearing them. The stability fields of these minerals are related by phase diagram. Being a very important mineral in metamorphic petrology, the pressure temperature stability of the aluminum silicates has been extensively studied. However, problems with establishing the PT field for these polymorphs include the aluminum silicon order disorder in Sillimanite and small compositional variations of these minerals. It has been shown that small amounts of iron and or manganese entering the structure of Andalusite may significantly affect its stability conditions. The aluminosilicate polymorphs Kyanite, Sillimanite and Andalusite are characteristic minerals of medium to high grade palitic metamorphic rocks like mica schist, biotite, gneiss and hornfels. Andalusite is commonly found in contact metamorphic areoles of shallow and intermediate depth intrusive and also in rocks subjected to medium grade metamorphism at relatively low pressures. Sillimanite is restricted to rocks that are subjected to higher temperatures and kyanite is characteristic of rocks subjected to relatively high pressures. Based on the bulk composition of the rock and grade of metamorphism underwent by a rock, these polymorphs may be found to be associated with cordierite, sterolite, garnet, chlorite, muscovite, biotite, plagioclase, potash feldspar and chloritoid. Eclogites, an ultra high pressure metamorphic rock, are also known to contain kyanite in association with pyrope-rich garnet and omphacite pyroxene. These polymorphs are not stable in a weathering environment, even though may occur as important detrital minerals. These polymorphs are less commonly also being reported from granites and granitic pegmatites. It is debatable whether they are of primary magmatic minerals or product of post-magmatic crystallization or are genocrysts. Genocrysts may originate from partially assimilated metamorphic wall rock or could be relics of the rocks from which the magma was derived by partial melting. There exists no compelling evidence as to why these minerals cannot crystallize from magma of appropriate composition under appropriate pressure temperature conditions. However, one should evaluate each case based on field, textural and related chemical evidences thoroughly. Now, we will discuss about the use of these minerals. On heating the aluminum silicates to high temperatures, it gets converted to mullite plus quartz. Mullite is used as a refractory mineral. Mutualized aluminum silicates find use in manufacture of refractory materials such as high alumina bricks and related products used to line blast furnaces and kilns, and in applications requiring resistance to temperature. Andalusite also finds use in manufacture of ceramic products, abrasive and filler materials. Here we come to the end of episode. Hope you like it and found it useful. Take care and goodbye.